Thank you, Dave. Can everybody hear me okay?
Yes.
Folks in the back? Okay. As Dave said, I noticed when I was putting together my talk, I've actually given 3 seminars to Mizzou since COVID, but this is my first time to actually make the trip, so it's really nice to be here. And also to reiterate what Dave said, I understand about 50% of the population here is from the public, and we've got about 50% of science people. So I'm going to try to stay at a high level. I'm going to do a couple of deep dives into our work, then I'm going to come back out at a high level. But ultimately, what I'm hoping to sort of articulate is sort of the title of things that we can do that are actionable to both live longer and live stronger. That's actually the tagline of the research institute that I direct, is live longer, live stronger. We're folks that study a lot of things about muscles and bones and those kind of things, so a lot of it's going to be tied to that aspect. Now, this is Olga. Anyone want to guess how old Olga was when this was taken? 83. Olga was 92 years of age when this photo was taken. Olga Koletko, she passed away at age of 95. When she was 90, she was long jumping, I think it was 5 feet 10 inches, almost 6 feet long. When she was 95, she was still long jumping over 5 feet. So I love to start with this photo because it sort of highlights that upper end of what we are capable of in terms of living a really healthy, long lifespan and health span. Now, I'm going to contrast that. That is not what I have lived. That was not my personal experience. This is me back in about 1979 down here with my family. This is my great-grandmother who was 88 at the time, but had been disabled. She was so weak from the age of about 80 that she could not live independently. She died. She had a long lifespan. She lived until she was 95. But the last 20 years of her life were not good. She was extremely weak and unable to have good mobility in the community and things of that nature. This was my grandmother. She developed Alzheimer's disease in her late 70s, early 80s. My grandfather passed away of metabolic complications when he was in his early 70s. So all to say, Olga is not the lived experience that many of us have had. This is probably our more common lived experience in the United States. It's so common that it's satire. How many of you have seen The Cat in the Hat on aging? Right? I cannot see, I cannot pee, I cannot chew, I cannot screw. Oh my God, what can I do? My memory shrinks, my hearing stinks, no sense of smell, I look like hell, my mood is bad, can you tell? My body's drooping, have trouble pooping, the golden years have come at last, the golden years can kiss my ass. I mean, it's a common comedy kind of thing, right? That this is what many people's experience are. What I want to do is try to give you some practical tips on what we can push to become more like Olga. Unfortunately, as I've kind of alluded to, that is not where we're starting. You're looking up here at the life expectancy amongst wealthy countries. Up here at the top, you have Japan, that today, there's a little bit of typo here, but today is pushing out to nearly 85 years of age for their average life expectancy. The average of high-income countries is about 83. The United States is pushing, now this has not been updated. We did just have a slight uptick in the most recent data, but this hasn't been updated from that, but we're at 77. And there's something else that I want to point out. See this dip right here? We know what that was, right? That was COVID. But what I want to point out is that we took a much bigger dip than the rest of the world. And a lot of that's because we went into it in a poor health state. In COVID, in my mind at least, it largely sought out vulnerabilities and exploited them. If we look over the past century or so, if we adjust for the contagious diseases, we've not seen much of a change in life expectancy. So we've somewhat stalled as it relates to extending our lifespan. Now that is particularly concerning, particularly in my mind as it relates less about how long we live, but about the quality of life that we have until the end. And as someone who is very interested in aging, this is what we're looking at, right? This is, folks, my age and up that's in this room over the next, 40, 25, 30, 40 years. We're going to see what I refer to as the silver tsunami and what a lot of people refer to as the silver tsunami. And what I really want you to focus in on is the proportion of people in the coming decades that are going to increase in this 80 to 85 plus year of age range, right? This is when we really start to see things like fractures become deadly. It's when we start to see things like muscle weakness become rate limiting. In fact, by the 2060, we're going to nearly triple the number of people in what we refer to as the oldest old category. That's 85 plus. And again, I've sort of alluded to this, but my interest is not in how long we live. What I'm interested in is extending what we call the health span. So this is sort of our current paradigm that many of us are probably used to. The lifespan, how long we live, is sort of shown here. And we sort of have a health span, and then we treat disease, and people live for a long period, but they've got a lot of diseases, and they may not have the highest quality of life. What I'm really interested in is how do we prolong the health span, that period of time before we have over-disabling disease that impacts our quality of life, and basically to extend functional capacity and reduce that time lived with disease. And we largely focus on muscle health and bone health. Dave sort of mentioned at the start that about 20 years ago I coined a term called dynapenia. Today, how many of you have heard of the term sarcopenia? Okay, what is sarcopenia?
Oh, you're just on the edge of having fragile bones.
So fragile bones, what do some other folks think?
A loss of lean muscle mass.
Loss of lean muscle mass. Okay. Bone fragility is osteoporosis. So close, right? Sarcopenia, osteoporosis, sounds similar. Loss of lean muscle mass. That is where we started. That was the original definition of sarcopenia, was the loss of lean muscle mass. Today, if you actually look at the most recent consensus definitions from most working groups, the primary characteristic of sarcopenia is muscle weakness. We've pivoted away from the loss of lean muscle mass. Muscle mass is still very important. We're going to talk a lot about that. But when I'm talking about sarcopenia, I'm going to really be honing in on age-related loss of muscle strength, loss of the function of the muscle, of which one of those culprits is the wasting of the muscle. But we're going to go a little bit beyond that. And we're also interested, so that's the muscle part, we're also interested in the osteoporosis part. We're interested in the bone health part. It's why I call my laboratory the neuromusculoskeletal laboratory. That's 3 different systems: the nervous system, the muscular system, and the skeletal system. We call it the neuromuscular part because our sarcopenia work is focused both on the nerves that control the muscles as well as the muscles, and our bone work is focused on the bone part, but muscles load bones. So it's an integrated system. How many of you guys remember the little cartoons when we were in grade school and every other thing about the hip bones connected to the knee bone and all of those sort of integrated systems? That is the body, and it works that way. We're interested in understanding the mechanisms that cause age-related changes in muscle function and bone health. We're interested in developing biomarkers as well as identifying effective, easily to implement interventions to promote muscle health and bone health. Now, I should state, because I think it's appropriate to state, I should declare some conflicts of interest here. We've been extensively funded by the National Institutes of Health, so I think those folks, that's less of a conflict, that's more of a thank you up front for keeping the lights on. I do have conflicts of interest with a variety of pharmaceutical companies. I'm not going to present anything related to pharmaceutical work today. I also have a conflict of interest tied to a company called OsteoDX, which I founded, and I currently serve as the Chief Science Officer. I am going to talk about that work. So when you see me talk about that, keep in mind that I have a conflict of interest with it. So let me start with the sarcopenia angle. Why does sarcopenia matter, or why does age-related loss of muscle strength and function matter? It's pretty darn simple. Physical independence has a strength threshold. If you do not have enough strength, you cannot get out of a chair, you cannot climb a flight of steps. Amongst older adults in the US, around 35% of women and 20% of men are unable to lift or carry 10 pounds. 10 pounds is roughly a gallon of paint, to give you a sense of what 10 pounds is. So it's not a lot. So you can imagine that if you can't carry 10 pounds, you're going to really struggle to get your groceries in from the car. You're going to really struggle to live independently. And if you look at the nursing home admission rates in the United States, a large proportion of people who end up in nursing homes are there because they do not have enough muscle physical function to live independently. Now, what people don't always recognize is there's actually a pretty darn strong association between how weak someone is and their risk of both death and disability. I think we all probably think, yeah, I can see that if somebody doesn't have enough strength, they're at risk of disability. Sort of that strength has an independence idea, you can't climb the flight of steps. But weakness is actually also mapping to premature death. This is a study that we did in collaboration with a colleague at the University of North Dakota, where this was a causal matched cohort study. So the people who we were defining as weak were matched for their same disease states as those who we were defining as strong. This was data for the scientists in the room. This was data from the health retirement study that comes out of the University of Michigan with nearly 20,000 individuals. And what I want you to notice is that when we track these people over an 8-year period, the likelihood of survival is on the vertical axis here. Notice that the likelihood of these weak older adults surviving is much less. They're dying prematurely. In fact, it's a 54% higher mortality risk than compared to an older adult who is strong. There's also data suggesting that that statistic starts in midlife. So when someone's in their 40s, it even maps forward. So when I had asked what the definition of sarcopenia was at the start, someone said the age-related loss of lean mass, and that is where we started. I started into this field in the mid-2000s, I'll say. I started graduate school in the late 90s, and when I started graduate school until the mid-2000s, that is exactly how we conceptualized sarcopenia. We would do things such as MRIs to quantify how much muscle someone has, or an X-ray kind of scan to quantify the amount of lean mass. And in this particular image, you can see the bone is in blue, the fat is in orange, and the red is the muscle tissue or the lean mass tissue. And 20 years ago, 15 years ago, the field largely viewed sarcopenia as the age-related loss of muscle mass, and that loss of muscle mass is what was causing reductions in force and power output of the muscle, and that was what was driving forward, causing weakness as we get older. Now, I'm going to talk a little bit of the work that's been done and try to help reframe why that's only part of the story. And I'm not saying it's not part of the story, but it's not the entire story. And so Dave mentioned in the intro talk that I had coined a term called dynapenia. So this was about 20 years ago. Myself and a colleague that I actually went to grad school with, we wrote a series of papers. The first one was called Sarcopenia Does Not Equal Dynapenia. And in this paper, we argued that the mechanisms of age-related loss of muscle strength are much more complicated than the simple change in how much muscle you have. And effectively, we were arguing is that we had been barking up the wrong tree and that we were not paying attention to the nervous system. I frequently call the muscles puppets of the nervous system. Right? If you have a spinal cord injured patient who does not have an intact nervous system, you get nothing out of the muscle. I mean, that's the extreme example of how you have to have a functioning nervous system for the muscles to work appropriately. And let me just sort of show you some of the work that's been done. I apologize, some of the slides. I use a Macintosh. I'm an Apple guy, so sometimes when we go to PCs, things get a little off. But to convince you that there's more to the story. So the data on the left is what happens if people go out and test a lot of people cross-sectionally. So we test everybody in this room, and we've got people ranging from, say, 20 to 85, and we do, I think this particular study did CT scans of the muscle to get how much volume the muscles are. We test everybody's muscle strength by seeing how much force you can produce or how much weight you can lift one time. And what I want to point out is when we look at data like this, over the course of the life, the age span, the muscle, if we test 85-year-olds and compare them to 25-year-olds, we tend to see that there's about 25% less muscle in the 85-year-old. But I want you to notice that we're seeing, more than a 50% reduction in the muscle strength. So there's a lot more strength being lost than just muscle. Now, this data in the right here is actually what we see if we track the same person over a 5-year period. So if we take people, this particular study was tied to the Health ABC study published by Matt Delmonico 15 or so years ago. And they tracked individuals over a 5-year period. Everybody was between 70 to 79 when they were first tested. They came back 5 years after that. And now this is not all the subjects, but amongst the subset of people, about a third of the individuals actually gained muscle mass during that time period. So these were people who were maintaining their muscle mass. They were not losing it. And if we look at these individuals who actually maintained or slightly increased their thigh muscle strength or their thigh muscle volume, they still lost a lot of muscle strength. So preserving that muscle did not necessarily equate to preserving the muscle strength. Now, this data here is actually from a clinical trial that we did at Ohio University about a decade ago. It was also from an investigator at WashU in St. Louis and a group out of Harvard and Tufts in Florida, where we gave individuals a compound that was designed to try to increase muscle mass. For the scientists in this room, this was a phase 1b myostatin inhibitor trial from the Regeneron compound that you may be familiar with. Myostatin is a gene, and if you express a lot of myostatin, that effectively means you express a lot of the protein, and that protein keeps the muscles from growing. And so we were basically trying to suppress that gene and that protein so that the muscles would not would grow. And what I want to point out in this study, we actually did see a 4% increase in muscle mass in the people that took it. But you'll notice that all of these lines are overlapping. So what that's telling us is, if we look at the placebo group in black versus the group that got the drug in red, there's no real difference, right? Even though we were able to increase the muscle mass with a myostatin inhibitor, we were not able to detect any significant or notable increase in muscle strength. So I only say that I'm not downplaying muscle. I cut my teeth as an academic studying muscle. I'm a big proponent of it. I think muscle health is very, very important. It has huge implications for your metabolic health. But I'm pointing this out to also just convince you that there's more going on that's determining why we lose our muscle strength as we get older than just the simple loss of muscle. And I'll go back. I earlier said that I conceptualize muscles as the puppet of the nervous system. I'm not the first person that conceptualized that. There's a guy named Charles Sherrington that every scientist in the room is going to know. Charles Sherrington was a very, very famous British neuroscientist in the early 1900s who won the Nobel Prize, I think in 1920. Does anybody know when Sherrington won? I think it was 1920. So we're going back more than 100 years ago. Sherrington said, muscles are merely good servants of the nervous system. And so what a lot of our work is focused on is trying to understand what's going on in the nervous system as we get older that makes our muscles get weaker. Now, you may be wondering, how do we go about determining whether your nervous system is activating your muscles effectively? So what we do is I work with humans. I'm not an animal guy, so we bring folks like you into our facilities in Athens, Ohio. We've worked with folks as late as 99 years of age off the top of my head. We have them sit in a machine that looks like an exercise machine that they can push out on, and we measure their strength. They just push out on it as hard as they can. It's pretty simple. Now, while they're doing that, we'll place a couple of pads on their leg, and we shock them. We literally just have a little machine. We can push a button. How many of you have ever accidentally shocked yourself plugging something into an outlet? Okay, it's very much like that. It's not as bad as that in a way, because when you do that, by the time your brain registers it and you pull away, you've had your finger on that shock for probably a quarter of a second. These shocks are lasting 250 microseconds, so they're very, very short, but they feel just like a shock. So what we do is we have someone push out as hard as they can, and in this particular example, the subject is pushing out, and you can see, as you would expect, if you push out as hard as you can, you're going to plateau, right? You're going to hit your maximal force. And then while they're doing that, we shock them, and we see how much the force goes up. For the scientists in the room that want to know the nuances, this is a 100 hertz doublet, so we actually give two of them that are separated by 10 milliseconds, so it's a good little pulse, super maximal. We measure the force that goes up here, we have them rest, and then we deliver that pulse again, and we express how much this goes up relative to this to calculate like 80% activation, or I can also express it the other way and say you've got 20% of your muscle that you cannot activate. So it's a pretty gross technique. It doesn't tell us where the dysfunction in the whole pathway is going, but it's a way to assess how well your nervous system is activating your musculature. It's what we refer to as quantifying voluntary inactivation. And it's an index of how well the spinal motor nerves, so in your spinal cord you've got all these nerves that branch off that control your muscles. It's a way to assess how well you're able to activate those, as well as how well you're able to make those fire at a fast rate. And so when we bring a bunch of people into our lab and we test them, there's two take-home here. One, if we compare older adults to younger adults. So this was a study where we brought in a bunch of college-age students, and we brought in, each of these dots is a single person, so we brought in, 80 or 90 older adults, and we tested them. What I want to note is that there is no significant difference between the young adults and the older adults. So we do not see a systematic difference. Now, you'll probably looking at this and saying, but I see a bunch of data points up here and not down here. I'm going to get to that story in a second. But across the board, we do not see a difference. Now, if we take these same older adults and we say, this person is strong, this person is weak, and this person's in the middle, right? We've done a lot of work, so we have various clinical cut points of what we will consider to be clinically meaningfully weak versus strong, just like with blood pressure and other, kidney function values. We have normal values and things of that nature where we can say somebody's got high function or low function. So when we take people who are strong versus those who are not strong, what we'll see is these weak older adults have higher levels of voluntary inactivation, meaning their nervous system is not activating their muscles well. So take home from that is it's not inevitable, right? We're not seeing it with everybody. In fact, if you look over here for these not weak older adults, their value is near identical to the 20-year-old kids. But for those who are weak, that nervous system activation seems to be really important. We've also done work, now we're going to get a little bit more mechanistic. This is when I'm going to start taking a little bit of a deeper dive for the scientist in the room, where we look at the firing rate, how rapidly these motor units are able, or these motor neurons are able to fire. And we do this using high-density surface electrode arrays where we place recording electrodes on the muscle and we record them while people are pushing out. And then we effectively use AI-based decomposition algorithms to identify the motor unit firing rate. The take-home here is that when we go back and we look at these weak older adults versus these non-weak older adults again, particularly at high contraction intensities, we observe that the weak older adults' firing rates are about 3 times per second slower than the strong older adults. So about running from about 23 times per second or 23 hertz for the non-week older adults, and it drops to about 20 hertz or 20 times per second for the week older adults. Now, 3 times per second doesn't sound like a lot. 23 to 20 seems not a big deal. But when we do computer modeling to try to estimate how much that actually causes the force to go down, that's going to actually reduce the force up to 26%. So that 3 times per second firing rate could have up to a 26% reduction in your maximal strength. So that's the difference between getting out of the chair, climbing the steps. That's a big difference. Right, you can imagine that if I could do something tomorrow that makes me 25% stronger, that's a lot, right? That's, if anybody watched the Winter Olympics, that's the difference between a gold medal and probably last place in most sort of high-end professional athletic events. Now we're going to keep taking a little deeper dive. So what I'm showing up here, this is actually a staining of a motor neuron. So in your spinal cord, the very first part of the nerves that branch off, it's called the dendrites in the cell body of your motor neuron. These little blue things are the neuron, and this is the little branches that it's reaching out to get sensory input or input from other parts of the nervous system. And these little magenta colorations are serotonin receptors on the motor neuron. Now, what I'm trying to tell or sort of walk you through is how many people, when you wake up in the middle of the night and you go to the bathroom, you feel like it's a Herculean effort to get to the bathroom because you're weak and you're a little low arousal state. Okay? Nobody's raising their hand, but I'm pretty sure everybody's that way. I certainly am, right? So, you know, we wake up, and one of the reasons for that is our monoaminergic system. It's the part of our brainstem and our body that sort of dictates arousal. It sort of goes to sleep at nighttime. And so these brainstem monoamines, they actually directly act on these motor nerves via things like serotonin, via 5-HT2C receptors. And these enable what we refer to as persistent inward currents. So these persistent inward currents are kind of like these little chaperones in the cells that are saying, come to the party, come on in, come on in. And if those chaperones are waving people in, it makes the cell more excitable. And when I talk about a cell being excitable, I frequently will talk about you've got 2 people walking down a dark alleyway, and I jump out behind a trash can with both people. One person may jump 3 feet in the air and be really scared. One person may barely move. That person that jumps 3 foot in the air was more excitable, right? They both got the same input, right? I kind of scared them the same, but we got a bigger response in the other one. And that's the take home of this slide, is that these motor nerves that we're talking about, these are not just passive nerves. These are active nerves. And the excitability of them can be modulated by sort of the degree of arousal or the degree of serotonin, these monoamines. And what I want to point out, the main take home, is that without these persistent inward current mediated changes in excitability, our muscle force would be less than 50% of its maximum. So these persistent inward currents and the degree of excitability of the nerve cell can change how much force your muscle can produce by more than 50%. So that's a lot, and that's sort of what this little figure here is showing, that for the same input you get more force with a higher excitable nerve. And so we can test this kind of stuff in humans. Again, sort of placing some little sticky electrodes on the muscle and recording the motor unit firing rates. And when we do this, for the scientists in the room, this is what we refer to as measuring delta F technique, where we basically have 2 different motor units. We have a test motor unit, we have a control motor unit. A person's performing like a triangular task, pushing out, coming down, and we look to see from when the test and the control unit kick on, when they kick off, when the test unit turns off, how much the change in the firing rate is, with the idea being that it's an indirect readout of the PIC-mediated gain. And when we do that, what I want to point out here is going back to that same sort of design before where I was showing, this is what we see in weak older adults, this is what we see in strong older adults. This is some data we did with colleagues in Australia, where instead of having strong older adults, we actually had older adults who were senior Olympic kind of athletes. These were high-end athletes that were training a significant amount. And when we look at this delta F measurement, or how excitable that motor nerve is, I want you to see that the sarcopenic older adults, so these are what before I called the weak older adults, have a substantially lower delta F, a substantially lower index of nerve excitability. Our control subjects are a little higher, and our older adult athletes are even higher. And so that sort of summarizes a bit of where we've come over the past 20 years. So when I started into this field, we thought that sarcopenia and age-related loss of muscle strength was the direct cause of age-related loss of muscle mass. We've pivoted away from that, and I think it's now well recognized that strength declines much more rapidly than muscle mass, and that one of the mechanisms, it's multifactorial, but one of them is that weakness is linked to incomplete neural drive that we can observe in these slowing of the firing rates, and that this slowing and firing rate is tied to a less excitable motor nerve, okay? Now that is where we were up until a few years ago. Dr. Arnold, I've been collaborating with Dave's lab for a decade now, back when he was at Ohio State and now at Missouri. I work with humans. He mainly works, as a physician, he works with humans, but in his laboratory, he heavily works with mouse models. And this is something that I think is a beautiful part of science, where we can do translational work, looking for how do things from the rodent map to the human and back down. And so now I'm going to present a little bit of the work that his lab has actually been doing, where we're interested to see whether or not we could give a drug that activates those receptors on the motor nerve. If I go back to this right here, these magenta colors are serotonin receptors. So we were interested in, could we give a compound that activates these receptors, and it's the serotonin 2C receptors, which are pretty specific to the motor nerve. Would that actually increase the muscle function and physical function in these aged mice? Now, this idea, nothing in science is a single person's idea. This idea actually started from a shared colleague of ours, Mark Rich, who's at Wright State University. More than a decade ago, Mark was interested in sepsis-related weakness. So most everybody's familiar with sepsis. Sepsis results in massive weakness, and Mark had done a study where I had identified that this one particular compound called lorcaserin, which is a 5-HT2C agonist, increased the firing rate and force in these septic rats. So what I want to point out is, if I look at this, up here is a septic mouse, and this is just their firing rate of their nerve. You can see that it's kind of periodically bap, 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 but it's not bap, 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 bap. It's just kind of firing occasionally. And you can see that it doesn't have a whole lot of force coming from the muscle. Then they gave it this 5-HT2C compound, and you can see that that motor nerve is now bap, 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 bap at a very nice rate, and that the force is much, much higher. And so that gave us the idea, could this work in aging? And so this is some data that Nathan Kerr, is Nathan here? Nathan here. Nathan's a postdoc in Dave's lab. Nathan did this, it was published last fall, if my memory is correct. Some really elegant work showing that if he took, I think these were mice, is that correct, Nathan? Aged mice, okay. Took aged mice and dosed them with lorcaserin, this serotonin 2C receptor agonist, that effectively you could increase the motor nerve excitability, and that it enhanced the, actually this particular slide is just showing what we would expect, that if we look at, we have older mice who have less excitability. This is showing that after we give them the drug, we increase their excitability, and that after we do that, it translates to an increase in physical function. They're actually able to enhance their muscle strength. And then this is some data that's just unpublished from Dr. Arnold's lab showing that if we chronically give that drug to the mice, that we're able to increase the amount of weight that they can pull up a ramp, and that if we couple it with resistance exercise training, so now we're not just looking at giving a drug, we're looking at coupling the drug with resistance exercise training, we get a synergistic effect with about a 20% increase in the muscle function that is tied to the drug and resistance exercise training. So to summarize sort of where we've gone, 2 decades ago, we've identified that strength loss is greater than we see with muscle mass. Weakness is linked to impaired neural drive, partly linked to slowing in motor unit firing rates. That is partly due to the excitability of the motor nerves going down, and that we can restore that functional readout using a therapeutic compound. So from sort of the next steps that we're interested in doing is we're interested in trying to optimize the intervention. For instance, doing more formal work looking at whether it synergizes with exercise, how safe it is. We're interested in trying to strengthen the longitudinal evidence in humans, so we'll bring individuals who we've already tested at Ohio back 7 or 8 years after we've tested them to see how these kind of changes map to long-term functional changes within the same person. And of course, our ultimate goal is to move this to clinic through an FDA pathway. Now, I want to not talk about drugs, though. I want to talk more about what we can do today. And my title here is Calm Today, Weaker Tomorrow. Do we have any geriatricians in the room? Okay, I love geriatricians. I'm a huge fan of geriatric medicine. One of the things that I love about geriatric physicians is they tend to subscribe to this philosophy of deprescribing is a part of good prescribing. They tend to look at it as, okay, people have been taking medications that have been added to their portfolio for a very long time. Let's take a fresh look at those. Some of the most common drugs that older adults end up on are sedatives. These are things like Ativan and Xanax and the benzodiazepines and some of those kind of things. And then most commonly for anti-anxiety. But all of those drugs effectively lower the excitability of those nerves. So there's a lot of things so when I talk about this, I've been talking up to this point about what can we do? What drug could we give that'll enhance it? But now I want to just pivot to the opposite direction and get people thinking about maybe you're actually taking meds that are having an unintended consequence. And this is some data that came from Williams, and not out of my lab, in the Annals of Clinical Psychiatry, arguing that if you reduce the sedative burden, you can increase and preserve physical function. So that's a little bit more of the action item that's actionable today. So now I want to pivot a little bit from muscle weakness to osteoporosis and bone health. So I don't typically have to hit this too hard, but fractures are extremely common. And if you look at the fracture rate over age, we tend to see that we have a dramatically accelerated risk of fractures as we get older. About 30 to 40% of women will experience a fragility fracture in their lifetime. About 20 to 25% of men will experience a fragility fracture in their lifetime. The economic burden of fractures is enormous. I think it's like $73 billion per year. So fractures are extremely common. They're painful, they're disabling, and they kill. About a third of people who have a hip fracture die within a year of experiencing a hip fracture. What people don't frequently understand, though, is that our ability to identify people who are at risk of having a fracture remains pretty poor. We have some tools, they're better than nothing, but we can do better. And what I also want to point out is that osteoporosis, while it's a disease of older age, it is a disease that begins in childhood. If you look at how much bone mass we accrue versus time, no surprise to anybody in this room, it takes nothing more than watching kids grow. Most of our bone is laid down in those pubertal years. So I say this for those in the room who have kids or who have grandkids. The time to intervene for osteoporosis is 10 to 20 years of age. 90% of our peak bone mass is acquired by age of 18. But for those of us who are well past the age of 18, we're sort of stuck, right? We're not stuck. We can budge this. I shouldn't say it that way, but we've got to make different kind of decisions. So the current way we go about assessing fracture risk is through a dual energy X-ray absorptiometry scan to assess the bone mineral density. Sometimes that's called a bone scan, sometimes it's called a DEXA scan. How many people in this room have had a DEXA scan before? Okay, it's a lot of people. I'm used to that answer, that's why I asked that question. What people don't realize, and I'm not discouraging you from, when I talk to the community, I always have to make sure I state this very clearly. I'm not discouraging anyone from not getting these scans, and I'm certainly not discouraging you from taking medications based on anything that I'm going to say. But more than 75% of people who fracture do not have quote-unquote osteoporosis based on their bone mineral density. This is data from nearly 15,000 individuals where they look to see for people who had normal bone mineral density, people who were in the gray zone of osteopenia, and people who had osteoporosis, what the fracture incidence was. And here, 80% of the fractures occur in the normal or gray zone, not in the osteoporotic range. So we are missing a lot of fractures. So I think the take home here is if you come back in the normal or osteopenia range, it does not mean you're out of the blue. In fact, most patients who fracture do not qualify for treatment based on DEXA alone. Now, there's a lot of reasons for that. One is you could have perfectly strong bones, but you fall hard and you're going to break a bone. So there's the noise reason. But another reason is that the density of the bone does not necessarily equate to how strong the bone is. So on this figure, I'm showing you bone strength versus bone mineral density, and you only get about 50% of the variability in bone strength being explained by the bone density. And you're probably wondering what these ones in red are. I'm highlighting this to show that we can have up to a 3-fold difference in bone strength for the same bone mineral density. You know, all of these individuals here effectively have the same bone density, but you've got a 3-fold difference in strength. So the bone strength reflects structural and material properties that are not being captured by that bone density measurement. And only around 20% of fracture risk reductions that tied to bisphosphonate treatment or drug treatment are explained by bone mineral density gains. And so this is what we've been doing at Ohio University for about a decade now, 12 or 13 years. What we're working to do is develop a new medical device that leverages what we call a 3-point bend test. We have a patient lie on a table, we stabilize the 2 endpoints, and you can see this little probe that comes down, and what you're hearing is vibration. That little guy right there is vibrating between 20 to 1600 hertz, 1600 times per second. That's the bzz, bzz, that's the changes in vibration. And it does that at 10 different points across the forearm. So it's about a 7-minute test that ultimately generates data that looks like this. And this little part right down here, you can see sort of this one slope and then this other slope or this other peak. Up here is the bone resonance. When we vibrate the arm, the bone and the soft tissue, the skin, the muscle, the fat, they vibrate back at distinctly different frequencies. This one here is the bone, this is the soft tissue. For the scientists or engineers in the room, we fit a 6-parameter model to it to estimate the mass, stiffness, and damping of both the bone and the soft tissue. What we're really interested in is how stiff that bone is. And what we're quantifying is the stiffness of the bone. So the DEXA scan is measuring the density of the bone, the chemical density. This is actually a direct mechanical test trying to assess how stiff the bone is. And if we do cadaveric testing, where we take people who have donated their body to science, I'm not going to show you any of the gory pictures, but we test them on that machine, and then we actually take the bone out of the body and we break it. We get extremely strong relationships between bone strength and bone stiffness, and that's what we're showing here. So it's a highly accurate way to assess bone strength. Now, everybody always wants to know is, why do we test the forearm? Why do we test the ulna bone specifically? There's 3 reasons for that. One is that it's ideally suited for a 3-point bending test. We can stabilize these 2 endpoints. It's a superficial bone, so it's the pragmatic reason. There's 2 scientific reasons, though, that are worth pointing out. One is that the mid-shaft of the bone, right here where we vibrate, is near entirely cortical bone. So your bone has 2 different parts. You have the hard outer shell, that's the cortex or the cortical bone. Then in the inside you have more of the spongy looking bone, the trabecular bone. If we were to cut my arm open here and look at it, it's almost 90 to 95+% cortical bone at that point. And as we get older, that cortical bone loss is what predominates. After about 65 to 79, the vast majority of bone loss is from the cortical, that outer cortical shell, and after the age of 80, it's nearly entirely from the cortical shell. So we've purposely vibrated at that point to try to really assess that cortical bone. And I should also note that forearm fractures are predictive of future hip fractures. So this is a study that we just completed about a year ago. It was just accepted for publication about 2 weeks ago. It's not even actually out yet. You can't get it on the internet yet. Where we had 372 women between 50 and 80. A third of them had had a fracture. 2/3 of them had not. Everybody got a DEXA scan. Everybody got this new test that I'm talking about. And there's a few take-homes. One is that if we compare the people who had fractures to the people who had not, we had about a 22% difference in the bone stiffness. It's a pretty big difference. Whereas if we looked at the bone density values, we only had about a 3 to 6% difference, hinting at it being a little more sensitive at assessing skeletal health. Then if we, that's a poor resolution photo, I apologize. If we look at how well it does at identifying those who had fractured versus not. So for the scientist, that's your typical area under the curve analysis. This black line here is a perfect 50-50 coin flip. All of these that are just a little bit north of that are the DEXA scans. These 2 that you can kind of see, they should be colored in a little better, but the orange one and the red one, those are the stiffness values that are coming from that new device that we call cortical bone mechanics technology. And we had about a 30% relative improvement in the discriminatory accuracy with the new technology. So this is sort of a summary of where we are today. We're using multi-frequency bone biomechanics to assess skeletal health. That's a pretty accurate measure of whole bone strength. And this technology seems to be improving fracture discrimination. Now, our next steps are to try and get approval from the FDA, try to develop a normative database, and continue the process to move it to clinic. Things like developing scalable manufacturing. We've got two engineers in Athens, Ohio right now that build these, right? We can't scale these up to a mass level, so we've got a lot of sort of commercialization tasks ahead of us. But we're optimistic that ultimately directly assessing that bone stiffness and capturing whole bone strength could improve fracture risk identification and address a major diagnostic gap in osteoporosis care. Now I'm going to pull back out of my deep dives and come back to the high level. What can you do? Practical tips for healthy aging. I put these here. I'm not going to dive into these, but if you are a smoker, please stop. I beg you to stop. It is a known risk factor for nearly everything. And I just put this here because we know that what we eat is very bad for us. But I don't want to dwell on that stuff too much. That's stuff that we know. So a few practical take-home tips. One is aging is not a straight line. There's a logical tendency to think about aging, if we think about our physical function or our muscle strength, sort of being a linear decline over time. It's not. What we probably see more often is someone has an acute illness. It could be the flu, they break a leg, they have a hospitalization, whatever it may be. They have a rapid decline, they start to recover, but I want you to note that they don't necessarily, well, this one they probably do come back to the linear decline. But what more often happens, somebody gets to here, but they never bounce all the way back. And so you end up with this rapid sort of stair step down. So I say that from the practical point of what matters a lot whenever you have one of these acute illness bounce or negative health event bounce is how well you bounce back, your resiliency, how much you recover. Physical therapy, I think I heard someone say that. Exercise, nutrition, I cannot stress it enough. If you've had some sort of a negative health event, do not be like my father, who is the one that gets ill or breaks his finger and refuses to do any rehabilitation. Go get it and get your values, your physical function, your stamina, ever how you want to quantify it, back up to where you were. Because if you have 10 of these and you only get back to where you were at 90%, after the 10th of those, you're a lot further down on the scale. Genes matter, but they don't decide everything. If you've never heard of the term of a gerogene, this is a term I just recently learned, and I really like it, right? These are certain genes that predispose us to certain increases in age-related diseases. I'll just use one because it's probably the most widely studied. Apolipoprotein E4, that is a gene, it's called the Alzheimer's gene. If you're a single carrier for the E4, I think it's a 2 to 3, maybe 4-fold increased risk of Alzheimer's disease. If you are a double carrier of that, only about 2-3% of the population, but you're at a 10 to 15-fold higher increased risk. So genes matter, and they're going to determine your ceiling, but lifestyle is going to determine how close we can get to that ceiling. So I say that for two reasons. One is know your risk factors, right? Understand. It's simple today. If you want to know some of your genetic predispositions, genetic testing has become doable. And then be smart about how you target that. Coming back to sort of the muscle and the bone aspect, they age together, and movement is the common currency. Exercise, physical activities. Some people will refer to sarcopenia and osteoporosis as two sides of the same coin because they're so intricately linked. So this is some data that we did at Ohio about when COVID hit, where we were comparing 3 different exercise interventions in older adults to see which one, if we took a very pragmatic approach, 3 times per week for 45 minutes, that's it. And we wanted to know, does resistance exercise training, does moderate intensity bicycling versus what we refer to as high intensity interval bicycling. So you bike really hard for a minute or two and then you rest for a bit and then you bike really hard for 30 seconds, sort of that intermittent, you're going to go hard, easy, hard, easy. Which of these 3 different exercise interventions have the most robust effects on your muscle strength, your muscle mass, your body composition, and your aerobic capacity, or your what people frequently will call cardiorespiratory capacity. And the one thing I want to point out is that notice the blue one, the resistance exercise training. In every single one of these, it exerted a profound effect. I'm not saying you shouldn't be doing the other ones, but if I can put in one plug for an older adult to do something, it's do strength training. It becomes more and more important as we get older. I'm less worried about it for a 20-year-old. I'm extremely worried about it for a 75-year-old. Resistance exercise training is a very, very robust and profound drug for aging. I always love this photo of growing old is not for sissies. This is a famous quote from 1978 by the director of the National Institute on Aging. If exercise could be packaged in a pill, it would be the single most widely prescribed and beneficial medicine in the nation. That still holds true today. We actually wrote an article about 10 years ago that gives a resistance exercise training program for anyone. I mean, we literally made it start for a 6-month period for folks in their 90s to start. If somebody wants that program, they can email me, clarkb2@ohio.edu. I'm happy to send you that article. It's a very step-by-step, lay public friendly approach. The take home though, Do your strength training at least 2 to 3 times per week. Focus on your major muscle groups. And progressive load, what that basically means, if it doesn't challenge you, it doesn't change you. You need to be working at a hard enough intensity that it's going to challenge you. Of course, you have to feed your system. As we get older, adequate protein intake is increasingly important. It's critical to building tissue and maintaining that muscle mass. We've not talked a lot about muscle mass, but I downplayed muscle mass to some extent, but it's extremely important. If you want to maintain your muscle mass with aging, it's extremely critical that you get the right nutrients. So eating good, healthy, real food. It's never too early to start. This is Rosemary. She died at 99 years of age a couple of years ago, but this is when she was with us and she had completed a 3-month-long resistance exercise intervention at the age of about 94. And I didn't quantify it, but if I had to guess, she went from this height to this height in that time period. And it wasn't that her bones were necessarily adapted, but her posture got better. And that's why if she looks like she's standing proud, that's why she was standing proud, because she kept talking about how much her postural control had improved. Childhood builds reserves, adulthood maintains it, and older age preserves it. So the take home, aging is not inevitable. It's not inevitable. Your muscles, bones, and nerves adapt to use. Exercise and nutrition are powerful. Recovery from illness matters. Small habits compound over time. Genes matter, so know your risk. For those of us who are over a certain age, you'll know Jack LaLanne. I always say Jack had it right. So for those who are under a certain age, you will not know Jack LaLanne. Jack was an ardent advocate, public health advocate for exercise, nutrition, physical activity for many, many years. He died in his late 90s and was exercising up until a few days before he passed away. This is not a quote from Jack, but motion is medicine, strengthens independence. There's 2 quotes from Jack that I really like. Dying is easy, living is a pain in the butt. It's like an athletic event. You've got to train for it, you've got to eat right, you've got to exercise. Your health account, your bank account, they're the same thing. The more you put in, the more you can take out. And then if you don't take anything home from this, just take this one home. If man made it, don't eat it. It's a really simple one, right? That's one that sticks really well. Just a few acknowledgments. I actually have several of my folks here today, a couple of PhD students that are here today. These are some of my current trainees, just selected former trainees that are involved in some of the data that I presented, and then some of my selected collaborators from Ohio University. I should point out Letha Clark, my long-term collaborator, and my wife. As well as Ann Laux and Lynn Bowman. They were deeply integral to the development of the early work on our bone mechanics technology. And I should also fully recognize Dr. Arnold's lab here at the University of Missouri, as well as my colleagues with OsteoDX and some other key long-term collaborators. These are my older adults in Athens that have done our studies for years. They literally give us their blood, sweat, tears, muscle biopsies. That list goes on and on and on. So we're super grateful for them. And I'm happy to take any questions. I always say at this time of the talk, I feel like this cat with the scientist ready to pounce. So.
To make it easier, just put your hand up and I'll make sure you get the mic.
Could you repeat your email again?
Yes, my email is Clark, C-L-A-R-K, B as in boy, 2 as in the number, at Ohio, like the state, .edu. clarkb2 at ohio.edu. I think she's got a microphone.
So I'm assuming when you said you're waiting FDA approval that the cortical strength testing is not covered by Medicare or insurance?
No, the cortical bone mechanics technology is not FDA approved. It's not been covered by any of those kind of entities. So no, it is not available at this point. Outside of, we have machines in Indianapolis, Ohio, Ohio State, and Oregon Health and Sciences University. So we have a few of them, but they're for research use only.
We got one over here.
I really like the way you present the nervous system, the bones, and the muscles as being a package, and that they're all important. I haven't seen in the research studies that you've shown how balance and coordination exercises, in addition to muscle strengthening. Muscle strengthening is absolutely important, but balance training and coordination exercises, I do think can train the nervous system
100%.
just the way, and you can improve that way too. So are there ongoing studies or studies that you know of that show a reduction in, like, say, hip fractures with balance and coordination training?
The short answer to that is absolutely. I 100% agree. There are studies. One of the most robust predictors of physical function in older adults is a simple test called the 4-square step test. You put 2 pieces of tape on the floor and you see how quickly somebody can do this into each block. I mean, that's a complex motor task. That is as predictive of negative health outcomes as about anything that you'll find. So I fully agree. There are all kinds of studies showing. Some of my favorite work is dancing. Dancing is a robust interventional strategy because not only do you get the motor coordination, you also get the social engagement. I did not talk about the importance of social engagement with aging, but we know if COVID's taught us anything, it's that if you isolate people, they deteriorate very rapidly. I think Dave's even got data in mice showing that if you isolate little mice, they deteriorate rapidly. And so things like dancing or things where you're doing tasks that build motor coordination and function with social engagement are huge.
I'm going to read one quickly online. What are your thoughts on how age-related or aging-related changes in the microcirculation affect muscle strength and the performance?
That I think is, so the question for the lay public is can you repeat it one more time, make sure I get it right?
Yeah, what are your thoughts on how aging-related changes in the microcirculation affect muscle strength and performance?
Okay. So that question is asking about the perfusion of the muscle, how well blood flow into the muscle affects it. I think it's critically important. I sort of tried to insinuate from the start that I think it's a very multifactorial process. I think the age-related loss of muscle mass is driving that reduction in function. I think the nervous system, I think the perfusion of the muscle, blood flow, the mitochondrial ability to produce energy. I think it's a very multifactorial integrated system.
Can you speak to muscle and structural flexibility and the importance of flexibility in aging?
That's another very under-recognized aspect. The range of motion, we see it with the people that we work with. I'm experiencing it myself as I get older. We lose a lot of range of motion and flexibility. I frequently recommend when I give talks to our older adults in Athens, yoga to improve flexibility. Be a little careful with certain poses. I don't want somebody to develop a vertebral fracture. But yeah, flexibility is huge. Dave, do we have time for one question? The geriatrician, and I said that I love geriatricians.
One more question, sounds great.
So, disclosure, 2 of my kids were Buckeyes at the Ohio State University. So the question is 1 in 8 US adults are eating GIPs and GLPs. That is like semaglutide and tirzepatide. And most of them are they're falling now.
Yep.
And I hear this all the time. What is your lab or your response in that? Because they're losing, when they lose 100, if they lose 100 pounds of weight, 30% of that is lean muscle mass.
Yeah. Yeah, so the question, everybody's heard of the GLP-1s, right? The weight loss drugs. The question's what's my opinion on the weight loss drugs as it relates to changes in body composition and fall risk. I 100% agree. John Batsis from the University of North Carolina, geriatrician, I don't know if you know John. John just published a paper in Nature Medicine. It was a commentary on this issue. It's a great article. Raising the red flag that as people are taking those, there's losing a greater portion of muscle and bone than they are fat. So your body composition, you may be losing weight, but your body composition is not changing in the way that we want to see, and it terrifies me. I'm not a physician. I don't like to tell people what to do and what not to do, but I am very opposed, generally speaking, to those weight loss drugs in older adults. Thank
So
you.
for the sake of time, I think we're going to wrap up. So Dr. Clark, I really want to thank you for sharing your work. This is a token of our appreciation. So this was made from lumber within about 10 miles from here. Has your name on the back there.
Oh,
So,
very nice.
5th anniversary speaker, thank you so much.
Thank you.
So please join us next month, and if you need help in getting registered, there's folks outside that can help you with that, and thanks for your attention.